My screen is visible to you. So in today's tutorial we'll solve the week 6 assignment that was given to you, and after that if there is time then I'll probably give a similar one more example sum to solve. Okay, so let us begin. This is now our week 6 assignment. Solution. Okay, so let us start with the first question, and let me go to full screen. So it is being asked in the question that we have an Ising model with a particular Hamiltonian structure given like this. Given like this, and you are asked that you are told that Sn plus 1 equal to Sn. That means your last spin value is actually equivalent to your initial spin value, that is S1. So it is kind of a periodic boundary condition, as if you are going like this in different spin values of S, like say it is S1 and then S2 and S3, and like this if you go round and round, and when you end up and reach the Sn plus 1th term, then you actually come back to this term only. So this is a generic rule people use in Ising type of models, just for the simplicity of calculations or for better understanding the complicated mathematics. So this is your periodic boundary condition that they have applied in the problem. Okay, and also it is mentioned that the SI values are possible to have two values, that is 0 and 1. So do not get confused here, because often you get that in real cases the spin values are either plus 1 or minus 1, but in this case, for the sake of the problem, it is 0 and 1. So we have to put the values correctly. It is 0 and 1 and not plus minus 1. And this I index is a dummy index. It can vary from 1 to n. This is actually the index that signifies the what is the spin that we are talking about, what is the spin moment we are talking about. This is the thing, and this Hamiltonian that is given here is actually an Ising model Hamiltonian, which deals with mainly the interaction term between the neighboring spins. Interaction between, not neighboring only, but nearest neighbor spins. Nearest neighbor spins. So this is because we are only dealing with this SI into SI plus 1 term. That means only the spin moment that is sitting next to the moment SI is actually contributing to the interaction, right? So that is why you are calling it a nearest neighbor interaction term. And we know that J is the interaction strength, where for a ferromagnetic case J will be positive and antiferromagnetic case J will be negative. And in the summation over 1 to n is actually not from J, it is actually from I, because our only index is I. So it is same as I equal to 1 to n. Okay. So all this is given, and the question is not probably framed properly from the structure of the answers, possible options that is given to you. You can take an idea that we are asked about the value of the transfer matrix for this Ising model based on this Hamiltonian. So what we need to derive is the transfer matrix value for this problem. Transfer matrix value. Okay, sometimes people denote it by T, sometimes people also denote it by P. So there are different notations for it. Okay, so we'll only follow one of them. One of the notations, we'll probably use T as the transfer matrix notation. Okay, so let us try and begin to derive how we can get the transfer matrix for this problem. So here question number 1, is basically so first of all, what is transfer matrix? You probably have read from the Ising model lectures of the course that transfer matrix is kind of a solution method that is used for solving this kind of Ising model case where you are given Hamiltonian, and basically it makes the problem easier to actually derive, and we just have to get the eigen values of the transfer matrix, and eventually it helps us to get the partition function for the system, which is our main aim. Once we get out the partition function, using that we can derive many more other quantities, right? So that is our aim. So basically, first of all, let us briefly define the transfer matrix structure. So let's say your transfer matrix is T S S prime, where S and S prime are two different spin moments. Then your transfer matrix element T S S prime, this is an element of transfer matrix T. This is equal to S T S prime. So this is similar to any other matrix moment, like matrix problems you have probably solved in mathematical physics course in your math physics classes maybe. So this is just simply defining a matrix element where if we are dealing with the S prime moment, then we have to write the element like this, where the matrix is in between and the eigenvectors or the states we are trying to deal with for the element is on both sides, like sandwiching the matrix from both sides. Okay, so this is the common definition of the matrix element for any matrix. And for let's say for you want to get the matrix element, transfer matrix element, that is the m and nth element, where the first like you basically for like any matrix you want to get the m and nth element, like m row and nth column element for the transfer matrix. Then what you do is that you just, the standard terminology is it is equal to e to the power of beta j m into n, where beta has a plus sign in front of it. This is for the case when your m and n value can be plus minus 1. So this is a generic case. Well, let's say m and n, that is a spin values. Spin values can take two type of values, that is plus 1 and minus 1, which is the most general case. Then you write down your transfer matrix element for the m and nth element. You write down like this. Okay, like an exponential of the involving the interaction strength, the beta, and the spin values. Okay, so if, and we know that transfer matrix can be a two cross 2 matrix if our spin values can take only two values. So it is a 2 cross 2 matrix if S, that is a spin, can have two possible values, which is true for our case because in the problem it is mentioned that the SI value can take plus 1 and 0, two values. So our transfer matrix will also be a 2 cross 2 matrix. So also if there are in some problem, if you are given three possible values of the spin, like let's say if you are given S can take values like plus 1, 0 and minus 1, then you have to know that your transfer matrix will be a 3 cross 3 matrix. So it depends, the matrix rank actually depends on your matrix dimension, actually depends on the possible values of the spin that you are given in the problem. Okay, and so how does the idea of transfer matrix first appear is that first let us try to write down the partition function for this type of problem, that is, let's say Zn. Z subscript n means it is for the system that has n number of spins. Okay, so this is the partition function of system with n number of spin values. So you write down Zn. Partition function is basically this, you know the form, that first of all e to the power minus beta, this is the Hamiltonian, and this bracketed S in the curly bracket is basically I mean to write down the all possible configurations of the spin elements, right? So basically you have to take the exponential of minus beta and Hamiltonian, and we are summing over the all possible configuration of the spin values, like even if the spin can have two possible values 0 and 1, but in the configuration of n spin items, they can be rearranged like any thing, like, right, like your first spin can take the value 1, then the second spin can take the value 0, or the other way around, or both of the spins can take the value 1. So similar to that, you have n number of spins present in your system, and each spin can take two possible values, right? So based on that, we try to imagine that there can be many configurations that is possible for the total spin system, and that is what we try to denote by this curly bracket in S. So this means that we are summing over all possible spin configurations for n spins, each having two possible values 0 and 1. Okay, so after this is done, now in the problem, you know, the Hamiltonian structure is given to you. So our Hamiltonian was like this: minus j sum over I from 1 to n Si times Si plus 1. So we replace it here. This is equal to sum over all possible spin configuration with the power minus beta, and this minus of Hamiltonian makes it plus. So with the power plus beta, and then j sum over I from 1 to n Si plus 1. Right. So now we have written down, we have put plugged in the value of the Hamiltonian in the partition function. Now we can break it down further, and so basically you have a summation in the exponential power. So you know that e to the power of a plus b is nothing but e to the power of a into e to the power of b. So anything that is present in terms of summation in the exponential power can be written down like this, where each power goes to on each of the exponentials, and they can have a product like that. So similar trick we also use here, that we separate out the summation, and instead of that we write down like a product term. So it is product of I from 1 to n, and then e to the power of beta j Si plus 1. Okay, so now comes the role of the transfer matrix. So we can always write down this kind of a structure like the element product of the transfer matrices. So we keep the product term I from 1 to n like that. So this means your product, right? You probably are familiar with the notation still. So this is your product. So you have changed the summation into a product, and this if you remember that this looks familiar, but beta j is Si plus 1. This looks familiar with your transfer matrix element for the spin of Si and Si plus 1, because you wrote down Tmn equal to e to the power of plus beta jmn if your spins are m and n. Similarly, if your spins are Si and Si plus 1, then you can write your transfer matrix element for that as e to the power of plus beta j Si plus 1. So that is what we have done here. And then so this thing, you know that you can break it down further like this. This is the product of what? This is, let's say we start I value from 1, so we get first term is S. Let's say we take S1, so Si for I equal to 1 is S1. So we let's say for the simplicity of notation, we take S1 as our 1 and S2 as our 2, and similarly we take the subscript as our this notation. So this is just for the simplicity of writing down the whole expression. So following that, we know that when we are taking the product, so we basically are taking first of all I equal to 1 and I plus 1 will be 2. So their product will be T12, because then it will be S1 and S2, right? So we are basically writing down only the subscript so that we do not have to write a long expression. And then the next product item will be when I value is 2, that means the next value is I plus 1 is 3, that means it will be T2 3, and similar to this T3 4, and as you continue like that, so the product also continues, and you get finally for when the final value of I is n, so you get the first term is n, and in I plus 1 becomes n plus 1. So basically you know that you now see that your this was your partition function Zn for the whole system, and this is actually getting represented in terms of the products of the transfer matrix elements. So this is the connection why we are trying to solve it when we are trying to solve the problem in a transfer matrix method. So we basically take the elements as a transfer matrix element, and we take the product of that. And not only that, because we have the periodic boundary condition, so n plus 1 will be n, that means our final term will not be t in n plus 1, but it will be t in 1, because our n plus 1 is equal to 1. Okay, so up to this this is done. And now so basically here up to this part I have written down to actually introduce how the transfer matrix is coming into the picture mathematically in the expression of the problem, or to deal with the problem. Now after we have done that, we can directly go on calculating the elements of the transfer matrix. So clearly, because transfer matrix T, let's say Mn, for the spin moments M and N, so this can be written as the elements can be so the elements can be like this, that if your first spin is M, then the first element will be like this, and then just like how you calculate matrix element terms in any math physics problem, nothing very different. So you have to get like that. And in this case our spin values are 0 and 1, so our M values will be 0 and 1. So how to get that is basically, and you know that this is equal to your, because you know the element expression, this is to the power beta j m squared, and this term will be to the power of beta j m into n, this term will also be to the power beta j m n, and the last term will be to the power beta j m squared. And for our case, the spin values are m and n equal to 0 and 1. So let us take one element at a time. So you will have to get t00, t01, t10, and t11. Okay. So basically now just plug in the value 0 and 1 in these terms. So first of all, your m is 0 and 0. So it is to the power beta j 0 into 0. Then 0 and 1, that means e to the power beta j 0 into 1. This term e to the power beta j 1 into 0. And the last term is e to the power beta j 1 into 1. So this is equal to e to the power 0 means 1. This is also e to the power 0. This is also e to the power 0. And this is e to the power of beta j into 1 means e to the power beta j. So the final expression becomes 1, 1, 1 to the power of beta j. So this is your final expression. So I think this was in your option number C. You have finally calculated your transfer matrix for this problem. Okay, given the Hamiltonian you are provided with, and the spin values are given as 0 and 1. Okay, so this part is done, and then probably you have to get the eigenvalues. What you have to you have asked next is the eigenvalue for the transfer matrix. So this is easy. You can get the eigenvalue of any matrix. You know that we'll use that to get the eigenvalues of this matrix. So what was the question? Let us go back. So this is done. This is option number C, matches with the answer. Then the eigenvalues of the transfer matrix are, you have to get the answer, where for simplicity e to the power beta j has been simplified, denoted as x. Okay, so simple, you have to get the eigenvalue and replace e to the power beta j as x. First of all, so you have to get the eigenvalues of the transfer matrix T. This is equal to 1 1 1 e to the power beta j, but because in the problem e to the power beta j has been asked to denote by e to the power of x, x, because in the problem it is asked that x equal to e to the power of beta j. So we replace in here so that we have a simpler notation. Instead of an exponential, we just have an x here, and we need to have the eigenvalues for this matrix. So we know the rule that determinant of the matrix, let's say T minus lambda I is the unitary matrix, is equal to unit matrix is equal to 0, is the rule you first apply to get the eigenvalues, where lambda is your eigenvalue notation taken for the matrix, T is your matrix, I is your like unit matrix, like say for 2D 2 cross 2 matrix it will be 1 0 0 1. Okay, and this is, you have to take the determinant of this whole thing, and that will be equal to 0, and from that relation you will get your lambda as the answer. Okay, so in our case, determinant of T minus lambda I means your T was 1 1 1 x minus lambda into 1 0 0 1. The whole thing's determinant will be 0. First of all, let us construct the matrix that is inside the determinant. It will be 1 minus lambda. The second term is lambda into 0 0, so it is this 1 minus 0 means 1. The third term is 1 minus lambda into 0, that means 1 minus 0, that is 1. And the last term is x minus lambda into 1, that means x minus lambda. And the whole determinant will be 0. Now you know how to calculate the determinant of a matrix. You just multiply 1 minus lambda into x minus lambda, minus 1 into 1 is 1, is equal to 0. And you get x minus lambda x plus lambda squared minus 1 equal to 0. So now we have to solve this quadratic equation, and you will get two values of lambda. So lambda squared minus lambda into 1 plus x minus 1 equal to 0. So this is your final equation, and you have to solve that. So you'll use the rule for solving this kind of a quadratic equation root. So x equal to so this is like x squared plus bx plus c equal to 0, and you know the rule that x equal to then minus b plus minus root over b squared minus 4ac. This is your ax squared by 2a. So this is your rule that you use to solve this kind of a problem, and you will use it here, where your lambda, your a value is 1 because lambda square is 1 into lambda squared, b value is minus 1 plus x, and your c value is just x minus 1. So minus b means minus and minus this cancels out, 1 plus x plus minus root over of 1 plus x whole square minus 4 into 1 is a, and c is x minus 1 divided by 2a is 2 into 1. So what you get is that x plus 1 plus minus, so we can break it down. So this is x squared plus 2x plus 1 minus 4x plus 4 divided by 2. Simplify it further. So this is just x plus 1 plus minus root over x squared minus 2x plus 5 divided by 2. So what will be your two values? One can be written down as lambda plus, which is your let's say half times x plus half times 1 plus x plus root over x squared minus 2x plus 5, and your other root will be lambda minus, which is half 1 plus x minus root over x squared minus 2x plus 5. So these are your two roots for this problem, and let us match our answer. So this matches with option number C, I think C. So this is the answer we have obtained. So so up to this is fine. Now in the third problem, it is asked for the canonical partition function for the above same model when your number of spins n is much greater than 1. So when you have a very large number of spin, then what will be the value of the partition function z? Now to answer that, we have to remember some parts that we have already solved earlier, that is up to this part. So up to this part, we obtained the mathematical connection between the partition function Zn and the product of the matrix element values. So now we have to simplify it from this point so that we can get how we can calculate Zn, because in the previous problem we have already calculated the matrix element and the eigenvalues of the matrix. So depending on that, we have to calculate the partition function Zn. Okay. Let me go to full screen again. So we have to get the partition function for this problem. Now as I was saying that we left the calculation at this point where our Zn partition function was equal to the product of the matrix element of the transfer matrix, that is first of all summation over all possible spin configuration, that is sum over this bracketed S, and then we had something like this, that T1 2 transfer matrix elements for 1 and 2. This is basically S1 and S2 that we in short write down as 1 and 2, and then like that 2 and 3, and it goes on like this, and finally T n and 1, right? So what does it mean if you try to break it down even further? So this means that your spin, all possible spin configuration includes that your spin number S1 can take value 0 and 1, spin number S2 can take value 0 and 1, and dot dot dot. Similar to this, nth spin can take value 0 and 1. And like that, you can also represent the matrix elements like this, T1 2, then T2 3 like this, and this goes on, and you end up with n T1. Okay, so this is, I have just written down the matrix element structures, nothing more. And once that is done, now one thing you have to be careful about, that when we are writing down any such form, that T23, that is matrix element for spin S2 and S3, and the next term is T3 for matrix element of spin S3 and S4, and you take the product of them because they are nearest, like they are the sequential terms in the transfer matrix. So you have a product, right? You have a product in all these terms. T12 is multiplied into 3, and similar to that, all the matrix elements are multiplied in this case. So when you multiply T23 with T34, and in the front you have this spin, let's say S3 summation, like one of these terms, because the next term here will be S3, right? S3 0 and 1, and dot dot dot, all the spins are here. So S3 summed over for 0 and 1, two possible values, and you have this kind of a form. Then you can just simplify it as T2, 4, because you have summed over the S3th element, and that is common in both the elements. So by multiplying the matrix elements 2, 3 and 3, 4 and summed over by the S3 values, you basically end up with the matrix element T24. So this is a general rule in matrix. You can, if you want, you can verify it whether it is true or not by taking a simple matrix element form. And let's say you take a simple 2 cos 2 matrix, and you try to get this product, and you try to see whether this actually works or not. So you'll see that it actually happens that when you are multiplying T23 and T34, because you have 3 common in both of them, and that 3 is basically your S3, which is summed over for the two configurations 0 and 1 that is possible for them. So we basically end up with that element T24. So this is a known fact, and that fact will be using in all these element products. So here, because your all the intermediate terms 2, 3, 3, 4, and all of them will have a common factor like this, and they can be simplified out like this. Only your remaining two terms will be your um, like first term and your last term, right? 1 second. Okay. So if you go by that, so basically let us first of all not take all the terms together. Let us first, S1 is as it is, and let's say T12 and T23. So you have 2 in common, both of them, and you can take the sum over S2. So what you achieve here is that first of all, in the bracket you will be having from 1, 2 and 2, 3, you will be having T13. So your S2 will be gone because that is summed over, and all other elements are here, like S3 is there and up to Sn is there. Okay, and so the next term will be 3 and 4, and the next term will be 4 and 5, and similar to that up to Tn1. So then you take the next two terms like 1, 3 and 3, 4, you have 3 in common, and you can take the sum over S3. So what you get is that S1, S3 will be gone, you will have then S4 and dot 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 up to Sn. So from here you will get T1, 4, and similar to this we can continue to simplify things out by taking the product, and finally you will, if you go on like that. So also we have forgotten one thing, is that when we multiply T12 and T24, so sorry, T12 and T23, so you are basically left with, we are basically multiplying two matrices, so it will not be T, it will be T squared, because you are multiplying two T matrix elements and you are summing over 2. So your matrix element now becomes 1, 3, but your product term will be having a T squared to match the dimension. Similar to that, when you are taking this multiplication with 3, 4, so we have indices as 1 and 4, but your product will be T cube, because you are taking a product of squared into T, right? And similar to this thing will go on up to the last term, and eventually you will realize that the only thing you will be left with at the end of this thing, because all these terms will be cancelling out, so Tn will also be summed over, so Sn will be gone, and finally you will be left with only S1 equal to values of 0 and n, and inside your matrix value will be T to the power n, because you will be multiplying n number of terms like this, starting from T to T square to T cube, and up to nth term you will be having a T to the power n term. So this is what happening in this case. And when you are writing down T to the power n, what will be the matrix element? So it is basically your 1 comma 1, because what will be your final element? Your final element will be just your n summed over, and Sn will be taken out on the summation, and this one and this one, the front and the end will be left. So your matrix element will be 1 and 1, and you will be having T to the power n as a power of the matrix. So it is like you have a new matrix, that is T to the power of n. Let's say it is a new matrix T prime is equal to T to the power n, and that element you have to take is 1 comma 1, where the possible values of S1 is 0, 1. So basically 1, 1 means, you know that this is basically signifying the spin element only. So it is basically T to the power of n S1 comma S1. So that is what the simplified notation was about. So this means that you basically need to take the trace of the matrix T to the power n. Trace means the sum of the diagonal elements. So let's say if you have the matrix T to the power n something like this sort, where you have 4 elements like this. So trace means you have to take the 2 diagonal elements and take the summation of it. because you have been asked to get the element of S1 comma S1. So by taking that, you know that you have to write down the expression of trace of the matrix, that is the sum of the two diagonal elements of the new matrix T prime equal to T to the power of n. Okay, so T to the power n is the subproduct of n T matrices, and it is itself another new matrix that we can define as T prime. So now you know from math physics rules that if your let's say T to the power n matrix has two eigenvalues, lambda n1 and lambda n2. So your trace will be lambda n1 plus lambda n2, where lambda n1 and lambda n2 are two eigenvalues of T to the power n matrix. And not only that, from the math physics knowledge of the matrices and their relations, you know probably that you can always represent a matrix as a diagonal matrix where the diagonal terms are only the eigenvalues. So any random matrix A, B, C, D you can take, and there is a specific processing that you can do, and you can basically change its form to be something like this: lambda n1, lambda n2, 0, 0. So your trace value will be just your diagonal elements are only the eigenvalues. So simply the sum of the eigenvalues is the trace of the matrix. So this is basically known facts about matrices and their relations. You can look it up from any math physics textbook if you have forgotten. But this is the case we are doing here, that you are asked for the trace of T to the power n matrix. So you take their eigenvalue summation, that is the diagonal element summation or the trace of the matrix. And only problem is that you know the transfer matrix T itself, its eigenvalues are calculated in the last problem as lambda 1 and lambda 2, let's say. You know the answer. But when you are asked a new matrix of T to the power n, there is a power, then this is the basic rule that the eigenvalues will also be increased by the same power. So if you know the eigenvalues of T as lambda 1, lambda 2, then the eigenvalues of T to the power n will also be known to you, because that will simply be the nth power of the same eigenvalues. So that will be lambda 1 to the power n and lambda 2 to the power n. So once you know that, you can write it down like lambda 1 to the power of n plus lambda 2 to the power n. So this is the rule, that if you have the main matrix's eigenvalues known to you, then you can take any power to the matrix and the eigenvalues of the new matrix will just be the same power rise on the known eigenvalues of the initial matrix. Okay, so up to this you get that your partition function is nothing but the summation of the eigenvalues of the new matrix e to the power n, where the summation can also be written as the eigenvalue of each transfer matrix T and their nth power summation, that is in lambda 1 to the power n plus lambda 2 to the power of n. So now the rest part is very easy. For problem number 3, you know we can start from this relation that we have just derived, and we can just plug in the values of lambda 1 and lambda 2 that we have derived in the problem number 2, and we have to use the assumption that your n value is much greater than 1, and we will be getting by calculating this, you will be getting your partition function. So first of all, your Zn is then lambda 1 to the power of n plus lambda 2 to the power of n, where if you remember your lambda 1 and lambda 2 values, you get that your lambda 1 is equal to, let's say we take the plus value in lambda 1, that is half into 1 plus x plus root over 5 minus 2x plus x squared. This is your lambda 1, and your lambda 2 is half the other root into 1 plus x minus root over 5 minus 2x plus x squared. So we clearly see that your lambda 1 has addition and lambda 2 has a subtraction. So lambda 1 will obviously be greater than lambda 2. And that means your lambda 2 by lambda 1, if you take to the one side, will be less than 1 because lambda 2 is less than lambda 1. And that means your lambda 2 by lambda 1 to the power of n, where n is very large number, will be very very small, tending to 0. If n is very large, that is n is much greater than 1, and given the fact that your lambda 2 by lambda 1 ratio is itself less than 1. So basically, if it is like, if you take a quantity that is less than 1, that is, let's say you take 1/3. Okay, 1/3 is a quantity that is less than 1. Now if you take the power of 1/3, with each gradual power your value decreases, right? Like if you take 1/3 square, that is 1/9, which is even smaller than 1/3. And similar to that, if you increase the power up to n, where n is very large and very greater than 1, then obviously it will be having a value that is so small that is almost negligible, and we can put it down as tending to 0. So that is the fact we will use here, that we can always take common lambda 1 to the power n common. So it will be 1 plus lambda 2 by lambda 1 to the power n. So this is your lambda 1 to the power of n, and because in the n much greater than 1 limit, using this limit you have got that this value, the second term is almost tending to 0. So your your partition function is just simply lambda 1 to the power of n, which is very easy. You just have to plug in the value of lambda 1, that is half into 1 plus x plus root over of 5 minus 2x plus x squared to the power of n. So this is your answer. This is, I think, your option number A. Does match. So you see that this is your answer that we have obtained. This is your partition function under this limit. N is much greater than 1, and this matches with our given answer. Okay. So this part is done, and we have 4, 5 and 6, 3 more questions left. So how much time is there? Okay, we have close to an hour left. So question number 4 is the question about the average energy of the system, of the same system. So we have been given a same Ising model system at the starting question, and all the rest of the questions are based on the same model up to at least question number 4, and then question number 5 you have a different model given. So question number 4 says that what is the average energy for the above system, and you are given 4 options. Okay, so as I told you that once you calculate the partition function for your system, then many more other quantities also becomes accessible to you, because based on the partition function value you can calculate the other quantities as well, like this average. So in this kind of problem, you know that average is actually taken and with the help of partition function. How? Like say you are asked about average energy, right? So in this kind of a ensemble problem, you know that average of any quantity, let's say here this case average energy, E average, is equal to, you have to take summation over all possible spin configuration, and then your energy is nothing but coming from the Hamiltonian itself, because Hamiltonian represents energy, and Hamiltonian of all possible spin configuration, H curly bracket S. Then as a weighting factor, as a weight factor, you have to add the value to the power of minus beta Hs. This is your Boltzmann weight factor, and below you have to write down the actual partition function form. So what does it become is that this is your sum over S to the power of minus beta Hs divided by Z, because remember this is your partition function value, so we do not write here Zn, So just simply Zn is written here as Z, so do not get confused on that. And then this is your Boltzmann exponential factor, as in weight factor. Okay, so basically on the numerator, if you look closely, you have to, it is just expression similar to this, that del beta of sum over s e to the power of minus beta hs and a minus sign on the front divided by z, because if you take e to the power minus beta hs sum and then take a derivative with respect to beta, so basically you take out the term minus hs to the front of it, right? And because there is plus sign in the numerator, so to cancel out that minus sign we have put another extra minus sign to the front. So this is the same expression, we have just written down the numerator in a different form so that it is easy for us to change modify the formula. So this is nothing but your z, this is your z, and this is your then minus del z del beta, derivative with respect to beta, and divided by your total z. So this is nothing but 1 by z del z del beta, which is nothing but your minus del beta of ln z. Because if you have taken a derivative of the ln function, you first take 1 by z and then the rest of the derivative is del z del beta. So this matches. So then you get what is the, how we can get the average energy, just using your partition function value z. So this is the relation, minus del beta of ln z you have to take. And now the problem becomes clear to you, that you have already in the last problem calculated the partition function value, and you have to take the ln of that function and then take the derivative with respect to beta, and finally you get the average energy, where so your z was half 1 plus x plus root over 5 minus 2x plus x squared to the power n, right? So this was your z from last problem number 3. So when you take a ln of that, simply take a ln and the n comes forward, this is the power. So n ln of half into 1 plus x plus root over 5 minus 2x plus x squared, right? Okay, and then you have to take the derivative with respect to beta, so minus del beta of ln z is equal to so this is minus del beta, that means you have to take a minus sign, and n is a constant, so it remains as it is. And remember here that here in this expressions x equal to nothing but e to the power of beta j. So you can change the derivative form, so that you first take the derivative with respect to x and then modify it with multiplying by del x del beta. So you take del x first, the whole thing ln of half 1 plus x plus root over 5 minus 2x plus x squared, then multiply it by del x del beta equal to minus n. Then you know how to take the derivative of a ln function, right? So this, the entire thing comes to the denominator, that is half 1 plus x plus root over the numerator, you have to take the derivative separately, so it is half 0 plus 1 plus, this is to the power half, means half 5 minus 2x plus x squared into 0 minus 2 plus 2x into del x del beta is your because x is e to the power beta j, so del x del beta is just j e to the power of beta j. Now we have to simplify these terms, that this is minus n times j, and replace this e to the power beta j again by x, so that the whole thing is in terms of x. So this is x into this half, and this half cancels out with each other. So you are left with this factor is 2 root over of, sorry, so this 2 5 minus 2x plus x squared has a 2 times x minus 1 in the front, right? And so you have this 1 plus 2 into x minus 1 divided by 2 into this thing, okay? And in the denominator you already have this 1 plus x plus root over of 5 minus 2x plus x squared term. So this 2 and this 2 actually cancels out with each other. So if you simplify, you are left with minus n jx into root over 5 minus 2x plus x squared plus x minus 1, this is the first term, divided by root over 5 minus 2x plus x squared. The second term is root over 5 minus 2x plus x squared plus x plus 1. So this is your ultimate expression of the average energy E, but you can always choose to simplify it even further if you are given options like this. So we'll also try to simplify it further, like this 5 minus 2x plus x squared. Then you can take this as, you can multiply the denominator by another 5 minus 2x plus x squared plus x minus 1, and then you multiply it by plus x, sorry, this was plus already, but you multiply with another extra minus 1 factor. And so because we have taken two such terms, so in the numerator you have to take a square of that. So this is then, so you're just basically trying to adjust the terms to simplify, whether we can simplify it or not. So this is the thing, and minus njx root over 5 minus 2x plus x squared. Then you can take a minus a plus b whole square or a minus b whole square type of relation, where a is root over 5 minus 2x plus x squared, so a square will be 5 minus 2x plus x squared, plus 2ab is 2 into b is your x minus 1 into root over 5 minus 2x plus x squared, plus b square is your x minus 1 whole square, which is x squared minus 2x plus 1. And denominator is, because this is a plus b into a minus b sort of a formula, where your a is up to this and 1 is your b. So this is a plus b into a minus b, which is a squared minus b squared, which is 5 minus 2x plus x squared plus x whole squared minus 1 squared is 1. So into so now we can simplify. 5 plus 1 makes it 6, minus 2 and 2, it is 4x, okay, and your 2x squared makes it 2x squared plus 2 into x minus 1 root over 5 minus 2x plus x squared. And the denominator is a plus b whole square, here is 5 minus 2x plus x squared, plus b squared is x squared, plus 2ab is 2x into 5 minus 2x plus x squared, then minus 1 as it is, okay. So this is minus njx divided by root over 5 minus 2x plus x squared into, this is then 4 minus 2x plus 2x squared, okay, plus 2x into root over 5 minus 2x plus x squared, okay. And so this part, if you try to cancel it out, so this we can write down as 4 minus, so the final form, let me write it down first. 6 minus 4x plus 2x squared plus 2x minus 1 root over 5 minus 2x plus x squared. But this can be your final answer, but I think in the problem the options are given in a different form. So here in the given option is this one. So there is njx that is already present in our term and in their terms also, so we do not have to do anything about that. And the denominator also have a root over 5 minus 2x plus x squared, which we also will not touch, so that this 3 term and this last term remains intact. And we have to simplify the rest of the terms so that it somehow matches with this minus 3 plus x root over this thing divided by 2 into 1 minus x. Let us try if that matches or not. So there is a minus sign to the front in our case. So you do not touch up to this term because this is already we got in common from our answer and the given option. Now for the rest of the terms, how we can simplify, try to simplify, is that let's say this above numerator term, we write it down as 4 minus 2x plus 2x squared plus 2x to root over 5 minus 2x plus x squared. What is the remaining term is plus 2 minus 2x, because this 4 plus 2 is 6 and minus 2 minus 2 is minus 4, and then you have 2x is gone, so it is just minus 2 root over 5 minus 2x plus x squared. Okay, so 4 minus 2x plus we can simplify it further. I don't know if we'll be able to match with the actual answer that is given in the options, because when I tried to simplify terms, I did not get the exact term that is given in the answer. So there may be a problem in the answer. Have you, any of you have already solved this problem when you have obtained the simplified terms matching with the given answer? If yes, then just unmute yourself and let me know. Otherwise, I'll have to assume that there is a problem in the answer, some typing mistake maybe, because I was not getting the answer that is given by them. Not anyone? Okay. If not, then we'll maybe leave it thing at here. This is our actual last simplified form up to which we could reach. And you can check it out that in the given term, given answer, we have common terms like this root over 5 minus 2x plus x squared and this x into nj part. So based on that, maybe we can match the option. But even if not, this is our answer that is we actually obtaining. Even if you do not try to match with the options only, this is actually the correct answer, irrespective of the option in the MCQ that is given. One can always choose to simplify it further and further as far as it is possible, but for the sake of the answer of the problem, I think this would be sufficient. And I think that the answer that is given in the simplified form is not something that I am getting when I am trying to simplify it. So I'll not proceed it any further, and any one of you also did not respond that you have got the exact same option matched with the given option. So we'll probably leave this problem here. It is actually your final answer. Do not bother about the option to match with, but this is your final expression in detailed elaborate form. Okay, and we'll move on to question number 5. Question number 5 and 6 are based on two different problems instead of the previous Ising model. So let us check that out. So question number 5 is that now for the above model, that model we are dealing with up to this point, now add a magnetic field to that model so that your H equal to now, instead of this only the interaction part that was present from before, now we have added a magnetic field which is plus H, and so based on that we have an extra term which is this H sum over I SI, and the effective mean field Hamiltonian you have to calculate. So this you have to use the mean field approximation. You have also learned about this from your lectures, the mean field approximation, what does it mean, but we have to apply this here in the problem. Okay, so let us write it down. So here Hamiltonian H is equal to minus J sum over I from 1 to n SI plus 1 plus H sum over I equal to from 1 to n SI. So this first term is from the interaction of the nearest neighbors, and the second term is from external field that is applied, external magnetic field. In this case H is the field that is applied. Okay, so you just have summed over all the spins and the magnetic field experienced by each spin is plus H, so like that. Okay, and so let's say from this generic Hamiltonian you have to get the mean field Hamiltonian from this expression, which is HMF, H subscript MF is your mean field Hamiltonian. Okay, so you can simplify terms in a specific manner. Let's say, so we have to get a mean field Hamiltonian, right? So basically what we'll do is that we can simplify the SI into SI plus 1 term with the HSI term so that the whole thing is modified in a different form. Okay, so what we'll do is that this, first of all, what is mean field approximation if you ask? So mean field approximation, if you can modify the term SI into SI plus 1 as, let's say, SI minus M SI, let me write it down first and then I'll explain what is the different term meanings. So this is SI minus M plus M, the first term. The second term is SI plus 1 minus M plus M. Okay, so basically we have done nothing but we have adjusted the M term as plus and minus in each of the terms in the product, where your M is the average, you can say this is the average magnetization, this is the average magnetization, which is defined as 1 by n sum over I from 1 to n SI average. So you can ask why there are two average signs. First of all, this SI average sign is for average over all possible configurations, where SI can take values 0 and 1. So this is that. And this overall sum and this divided by n up to this part is for the average over total n count of SI values. So there are two kind of averages going on over here. You have to take into account both of them, because this average is for the all possible configuration when SI can take 0 and 1 two values. And not only that, we have to also take into account the different spins, that is when I can vary from 1 to n, and you can take the average by taking a summation and 1 by n. So this is your average monetization, and this thing can be written as like that. So okay, this part is there. And then what is mean field approximation? So MFA, in short, mean field approximation, is to assume that fluctuations of spins away from average moment are very small. Where the average moment is, let's say in this case m, so whatever in each of the spins are not having the exact value as the average value, right? So your average value is m, but your individual spin value can take different values that can be different from m by some amount. But all mean field approximation is about that you have to approximate this thing, that whatever each spin is taking the value, whatever value they are taking, the fluctuation of that value from the average value m is not very large. Instead, that is very much small, or in some case negligible. So this is your mean field approximation. It means that if your individual spin value is SI, and your fluctuation of that spin value from the average monetization is SI minus m, is your fluctuation of SI spin from average spin value m. Okay, so if that is the case, so m is your, let's say, average over s. Okay, so this is your average monetization, which is defined here like this thing. So this fluctuation is very small value. This is under mean field approximation, this is assumed. So similarly, your any SI plus 1 minus m, this fluctuation for SI plus 1th spin will also be very small under the same mean field approximation. So what we get out of that is that we can always write SI into SI plus 1 term in the Hamiltonian as SI minus m plus m into SI plus 1 minus m plus m. So we can separate out the terms by multiplying each of the terms individually. So this is SI minus m, SI plus 1 minus m, plus m into SI minus m, plus m into SI plus 1 minus m, plus m squared. So what you see is that you have in the first term SI plus 1 into SI plus 1 minus SI plus minus m into SI plus 1 minus m, where each of the quantities is itself very small, because I just said that mean field approximation says that fluctuations of each spin from the average monetization is very small. So when you are multiplying two very small terms, so their product itself becomes even smaller. So even smaller when taken product of two small terms. So based on that, we can always ignore or neglect the first term to be 0, right? We can remove that by taking that it is very small and close to 0, and we are only left with this. So this is all an approximation. This is not in real case. We can always take some approximation to simplify our problem. So mean field approximation is like that. So mean field, why it is mean field? Because we are focusing on the mean value of the magnetization or the field, and that's why we are taking all the fluctuations from the mean value is very small, and we can ignore that, right? So, but when it is multiplied with the average value m, then m has a significant value. So we cannot ignore m into Si minus m. That has a significant value. And for similar reasons, we also cannot ignore the third term. So that those three terms actually remains. And what we get is that m into Si minus m squared. So we are separating it out again. M into Si plus 1 minus m squared plus m squared. So this m squared cancels out, and this is m into Si plus 1 minus m squared. So up to this we have obtained. So now once you have got that, so we can plug it in our Hamiltonian, actual Hamiltonian. So this was our Hamiltonian was this interaction term, and then the second term is plus h sum over Si, or h is the external field that is applied. So we have calculated the Si into Si plus 1 under mean field approximation. So this value we have obtained. So we'll just plug it in here. So this is minus j I from 1 to n m Si plus 1 minus m squared plus h sum over I from 1 to n Si. So again separate it out, is equal to minus j sum over I m Si plus 1 minus sum over j sum over I from 1 to n m squared, the second term, and the remaining term is this. Okay. Now there is an important consideration that we consider our total number of spins n is very large. That is actually also given in the as a consideration in some other previous problem where you are given this limit that n is much greater than 1. So we can actually take this consideration that there are a large number of spins present, and under this limit we can approximately say that our sum over of Si is nearly equal to your sum over of Si plus 1. That means if you take the sum of the spin moments for all possible value of I from 1 to n, so you just take the nearest neighbor spin value, which is Si plus 1, and take the summation of it for all the n values. And because n is very large, so that will not make much of a difference, and we can approximate that this summation is nearly equal to this summation. Okay. So as if we are taking that spins in the two nearest neighbor sides can be roughly taken as equivalent. Okay. So if that is the case, then you can write your h equal to minus 2j. So basically this term is equal to equivalent to this term. So this we combine it together, so this becomes a 2 factor minus 2j, and then sum over I m times Si. Under this approximation we have used, and the second term was minus j sum over I m square, right? But because m is an average value, so it does not depend on the summation or n values. So we can just take the summation up to n terms, so it makes it n times n square, because there are n times summation of n square value. So this is just j into n squared plus h sum over I Si, because here n is the total number of spin sides. Okay. So your h is just minus then j n squared. Then we take the two Si terms together, we combine them together. So what does that What can we write about that is that plus h minus 2j, because m is a constant, we can get it out of the summation, then sum over si. Okay, so this is your term, and then we can write this term as your h effective, where effective field can be written as h minus 2jm. So the effective field is actually the actual external field h minus a term that contains or includes the interaction strength j and the average magnetization. So by defining it like that, you get that your h mean field Hamiltonian is minus j and m square, a constant term first of all, which includes j, plus an effective field for each of the spin sides, which is h effective I si. So this is our final form. Why it is written like that is that basically because this is your mean field Hamiltonian, this has an interaction term present which involves j in the first term. So this is a constant term coming from, so nearest neighbor we short it in short write as in dot n, nearest neighbor interaction. And the second term is coming from your effective magnetic field experienced by each spin si, where H effective is actual external field H minus some interaction term of 2jm. Right, so this is the under mean field approximation. We have obtained this, and now we can actually modify it value so that we can get the final Hamiltonian expression as given in the formula.
This H effective is always positive, or
By age effective factor,
that is positive always, or because it is H minus.
That depends. That in our problem, H is given as plus HSI, right, in the main Hamiltonian. So in the main Hamiltonian, what we had been given in the problem is this one. There is a plus H factor. Sometimes in the problem it is given as minus H. So based on that it changes. Based on this problem there is a plus sign given. In textbooks sometimes there is a minus H given. So it all depends on what is the direction of the field that is being applied in this case. If there is a minus sign, then it actually will probably match with the answer. If
No, ma'am. I'm asking that last you calculated the that H minus. No, ma'am. What you calculated H minus some term is there, no? For H effective. That term whole can be become negative, or it always remain as positive.
too much noise. Can you repeat? I did not get your question. I did not actually get your question, what you are saying, because there is too much noise.
Ma'am, that H effective you calculated.
Yeah.
So there you have H minus some term containing J also, right? So whether that whole term can be always positive, or it can also become negative.
That again probably depend on what is the comparative strength of the interaction and the external field that is applied, of course, because what is the comparative value, relative value between the external field itself H and your J, what is the strength of J, based on that it will actually depend.
Yes,
Yeah, so that is actually how the physics will change based on what is, if your interaction is too strong compared to the field that you are provided, then it can sometimes make this H effective negative also. So that entirely depends on that. But
yes, that's what
yeah, so here if we proceed, so I was noticing that there is again a minus sign problem here also, because if I modify this, if I write it down as a, because we can always, this m square is basically what, this m is your average magnetization or spin, average of ace, right? So m square is nothing but your this ace average whole square, And is this n term is coming because we have already summed over the ith element, so we can always take out this n by again taking a summation of I from 1 to n, so that the first term now becomes minus j into m square is basically average s whole square, and this n is actually compromised with the summation of n because we have taken it inside the summation now. And then the second term has also sum over I common, so that we can write as h effective is basically h minus 2jm, so we write it down as h minus 2j, and m is average s. So this is this thing and SI, because this was your SI and a summation over I is to the front of it. So basically this is the answer I get as a mean field Hamiltonian expression. This matches with the option that is provided to us, it is except the minus sign that we are getting here. This is a minus sign that we have in our solution, but I think in the options this minus sign is not present, but otherwise the terms match. So I think this can also be a mistake in the options, so you can verify it by yourself when you solve it. You can see that there is no minus sign here. I think there should be a minus sign. Okay, so otherwise the answer will not match with any of the other things, because you see that in all other cases there is this 2h minus sj. This will not be answered probably because your h effective has itself h minus 2sj, so this part will have to be there. And then 2s whole squared is also not an option because there are no 2 multiplication, right? So the closest match to the options is this part, option number A. Only there will be a minus sign that probably they missed out. Okay, so this is the thing we have solved, and the final question is about the transcendental equation for the mean field solution of SI average. So not SI average basically because you see that the options are given as S average. So both carry different meanings. First of all, I told you that SI average means you are averaging over each of the spin elements. You are not taking the summation of all the I factors, I from 1 to n. So that is just the average for the possible spin values of 0 and 1. This is the individual average of SI. But when you talk about S average, that is equal to your average magnetization or average spin value M, and then you have this whole 1 by n sum over I SI average, because then we have to also take the total count of spin sides, so that we have taken sum over I and then divide it by n. So basically you have to get the solution of this S average or M, and then you have to match with this on one of the options. So how to get that? Basically, okay, so let me just go down. Yeah, question number 6. So in the previous problem you had been given the mean field Hamiltonian, you have solved for it. Okay, you have solved for the mean field Hamiltonian starting from the actual Hamiltonian that was given to you, and the mean field Hamiltonian comes as minus j n m square, if you write in terms of m only, equal plus h effective into sum over I SI, right? Now you know your m is nothing but your averages. This is your average magnetization or average spin, which is like 1 by n sum over I from 1 to n SI average. Now this we have written down earlier also, but what we have to know here is that it is also written as 1 by n beta del ln z del b. So here this is a specific terminology I have taken from a textbook. So where I'll tell you that this is applicable for a case when your energy or your Hamiltonian, let's say, for all possible spin configuration is given like this. This is a generic term. Okay, like let's say, first let me write down this. So let's say this is your Hamiltonian, or this ESI is nothing but the energy or the Hamiltonian for all the possible spin configuration, where the first term is for this bracket means you are only taking the nearest neighbor interactions. So this is same as what we have in our case. Only we have taken j instead of I plus 1, but when we are taking this sign, this bracket sign, that actually means that we are taking nearest neighbor interaction only. So it is equivalent to SI plus 1 sum over I. Okay, but the second term has this minus b. So here the external field that is applied is minus b. In our case it is plus h. Okay, so this is in our case minus b is equal to our plus h. Rest of all, if you compare, this is same as our original expression of h, because this is nothing but same as sum over I si plus 1, because I told you that this sign means that you are taking only nearest neighbor interaction, which is same as this. So based on this expression, generic expression of the Hamiltonian, you have this average magnetization formula goes like this, that 1 by n beta del ln z del b. So we have taken the derivative of ln z with respect to the field b. Now in our case, if you look it up carefully, then you will see that in our mean field Hamiltonian, in this case, okay, so if you compare with this, you'll see that age effective into SI is there, sum over SI, and here it is minus B SI. So to take it in terms of mean field Hamiltonian, you see that age effective equal to minus B. Okay, so because you will compare the mean field Hamiltonian with this value, not the actual Hamiltonian. And the first term actually comes from the nearest neighbor interaction, so you do not bothered about that. But this part is age effective equal to minus B if you compare this formula and this formula. So based on that, you have this general knowledge that this aim, if the general formula of this Hamiltonian, your aim is this, then you just replace B as minus age effective and you get the aim value for the form of our mean field Hamiltonian. So your aim is minus 1 by n beta del age effective of ln z. So I just told you how we are getting this, because this is a general known expression that when you have this kind of a Hamiltonian or energy term, then your mean average magnetization takes form like this, where this derivative with respect to field B is present. But if you compare this Hamiltonian with our mean field Hamiltonian, you get that age effective is equivalent to minus B. So we just replace this B as minus age effective, so that there is a minus sign in front, minus 1 by n beta, and this becomes minus del age effective ln z. Now you can ask me that how I am able to write down the previous expression only, how this part is coming, so that I will also show you, or you can also we will find it in the textbook also, but I'll show you in any case. So basically your aim was starting as 1 by n sum over I from 1 to n average SI, right? Now if your SI, the Hamiltonian in the previous general case is like this, as it's written, minus B sum over I SI, then your del E by del B, this derivative becomes minus sum over I SI simply. This has no problem. Now your average spin value, what will be that? Because we can always take the average, like we taken the average energy expression, so we'll use the same thing, that we take summation over all possible spin configuration and then the quantity SI, then the Boltzmann wave factor, that is e to the power of minus beta ESI divided by Z. So this will be, Z is partition function, so this is the average SI spin expression, right? But then your Z is the partition function, which is nothing but all possible spin configuration, then e to the power of minus beta E SI. So if that is the case, then this Z can actually be written as basically we are taking a sum over all possible spin configuration, right? So let us say if your spin configuration goes like this, then let's say this is minus e to the power of minus beta E for one type of spin configuration SI, and then the second type of spin configuration we can write it down as, let's say, psi prime, and it goes like this. So basically we are taking a summation over all possible spin configurations where each of the configuration value is looking like this. So you can imagine the factor like that, and you can take a ln. When you take the ln, so basically you take the ln of the whole this summation thing, right? E to the power minus beta, all the exponential part summation. So when you again take del ln z by del b, okay, so this is basically nothing but del ln z by del b, we can write it down as del ln z by del E. E is your Hamiltonian into del E by del B. So we can adjust it like that. So the first derivative will be taken on this whole term. So what you get is that from each term this minus beta will come out. So this is minus beta comes out from each term, and then the rest of the summation goes like in the same manner. Okay, and because there is a ln term, so always there will be a 1 by x kind of a term, so that gives you this to the power minus beta si plus this whole term. So this is because we are taking a derivative of the ln term. Okay, and this del b was nothing but your del b was minus sum over I si. So this is minus sum over I si. So what you get is that this minus and this minus cancels out with each other. So you get plus beta sum over I si, this part, this sum over I si part. And you have not only that, you have this whole term for all possible spin configurations. So how we can write it down combinedly is that you take the summation first for all the I values, and then you take the summation over all possible spin configurations like this, and then you take si to the power of minus beta e si. Then divided by this whole denominator is nothing but your partition function again. So this is z. So what you get is that this is plus beta, and then you get this is your all possible spin configuration average of si. So this is nothing but your si average, right? This whole term, because you are taking a wave factor of Boltzmann, that is this case, and dividing by the partition function, working on the quantity element si. So this is nothing but your si average, individual spin average, and this is taken for all I values taken in a summation I from 1 to n. So what you get is that this is your del ln z del b. That means your summation over I from 1 to n si average is your 1 by beta del ln z del b, or your m, that is equal to 1 by n sum over I si average is nothing but, is nothing but 1 by n beta del ln z del b. So we achieved the why we wrote down the expression for the general case of the Hamiltonian. This is your expression. So now this is proven that this expression is actually right. So now we can go ahead and just replace B as your minus H effective, because our mean field Hamiltonian, I showed you that our, if you compare, then you will see that this term and this term matches, and your minus B is equal to H effective. So replace this formula and get this formula. So we go ahead and use that formula. So for that there is a ln z expression. So for our case we'll first get what is z. So z is this sum over si minus equal minus beta H si, right? Then we write down the Hamiltonian as a mean field Hamiltonian here, minus beta minus j n m square. This is our mean field Hamiltonian value plus H effective sum over si. So this is your the per beta j in m square we take it out because this is a constant. So this comes out of the integration, and this whole summation term in the power of exponential, we know that we can take it out as a product, because I just in a previous problem I showed you that exponential summation can be taken out as a product. So that we do here, I from 1 to n as a product. Then inside you take this summation of the configuration, all sum of configurations, and then e to the power of minus beta H effective si. That is the second term here. Okay, so here, because si can only take two values, 0 and 1, so we can use these two values, we can plug that in, and we get e to the power beta j in m square as it is. Then sum over this product is as it is written, I from 1 to n. Then sum of the all configuration has only two configurations, 0 and 1, right? So we plug that two values one by one. First of all, when si is 0, this is e to the power 0, that means 1. Plus when si is 1, this is just 1, that means e to the power beta H effective, right? Now you see that this whole term has no dependence on I itself. So when you take the product I from 1 to n, it does not change anything, just it adds a power to the power of n, because you are multiplying the same quantity n number of times as a product. So what you get is that e to the power beta j in m squared, and then 1 plus e to the power of minus beta age effective to the power of n. So this is your z partition function. Now this is a pretty simple expression. So you get ln z, which is ln of this whole thing to the power n. So you so because you know that ln of a into b is nothing but ln a plus ln b. So in this case you consider this as a and this whole term as b. So dealing with the first term, you take out ln of a means ln of exponential this thing, which makes it just beta j in m squared, plus ln of b means this whole thing, so this n comes to the front, then ln of 1 plus e to the power minus beta age effective. So this is your ln z. Now if you take del ln z by del age effective, this derivative, first term is 0, the second term is n into, because this is a ln, so this is 1 plus the power minus beta age effective in the derivative, and then minus, sorry, this is 0, then because this is an exponential, so this is minus age effective e to the power of minus beta age effective. So what you get is that minus n, sorry, this was with
The
respect to,
beta, no?
yeah, this is beta. So this is just, then this is just beta. So minus in beta e to the power of minus beta age effective divided by 1 plus e to the power minus beta age effective. Okay, so you almost have reached the conclusion. So your m is minus 1 by n beta, this del ln z by del h effective. So you just plug in the value that we have calculated from the derivative. So this is minus n beta, and minus 1 by n beta cancels out with each other. Minus and minus makes it plus. So it is just beta, sorry, n beta cancels out already, so there is no n beta again. It's just to the power minus beta h effective divided by 1 plus to the power minus beta h effective. This we can further simplify as 1 by 1 plus e to the power beta h effective. So this is your final average magnetization or average spin m, which actually matches with the given option. If you just look at it, you'll see that, yeah, so this answer is there. So basically they have also changed the, now they have plugged in the value of age effective, so we can also do that to match the final answer. So they have plugged in the value here as 1 by 1 plus e to the power beta age effective is h minus 2jm. Okay, that is nothing but 1 plus e to the power of h minus 2, m is nothing but your average s into j into beta. Now this actually exactly matches with our option that is given. This is option number C, I think. So this is your option number C. So okay, so then assignment 6 is done with that. Let me check. So if you have any doubt regarding any of the solutions, you can let me know here, or else I am thinking that will not proceed anymore in this class. In the next class we'll deal with the final assignment, assignment number 7. I don't know if there is an assignment 8 is released, or there is up to assignment 7 only.
7 marks.
Okay, up to 7. So by solving assignment number 7, I plan to take another problem, that I'll give outside of the assignments, similar to these kind of problems where you deal with a partition function and then you calculate the average of some quantity. It will be a similar problem, but it will be a good practice. But today we'll not start that because that is a pretty lengthy problem. So we'll probably hopefully start that in the next class. So if you do not have any doubts anymore, we can end the class here and we'll meet in the next class. Okay.
Yes, class. Thank you. Nice class.